Hopefully my internet won't have any hiccups today.
Oh, are you in a different location?
No, I'm just hoping.
Yeah, sometimes that happens, but hopefully not.
Yeah, well, hey, you know,
Yeah.
you can just keep speaking for me and Adrian.
I'm sure it'll come back up. We'll be fine. I'll give it a minute because we have some people coming in, but
It's kind of early in the morning, though. You think about it for people on the West Coast, for example.
yes. I think the idea is because TSL membership is spread out in Europe and North America quite a bit to match both audiences. So yeah, it's not it's not the easiest time. People have said like let's do it 10 a.m. and so on. An hour here and there, or maybe a couple of hours. It has changed a little bit, but yeah, it still remains Friday mornings typically. Okay, maybe we'll start and people will keep coming in. Okay. Let me introduce our speaker for today. So welcome everyone to the monthly TSL seminar. This month we have the aviation section being represented, and as our speaker, we have Professor John-Paul Clarke from the University of Texas at Austin. He's a professor in aerospace engineering and engineering mechanics at UT Austin, and he holds the Ernest Cockrell Jr. Memorial Chair in Engineering there. Previously, he served as a faculty at both Georgia Tech, MIT. He was also vice president of strategic technologies at United, and a researcher of at Boeing and NASA JPL. He's been a co-founder of multiple companies, and most recently a company dedicated to developing a carbon-free solution for aviation called Universal Hydrogen. He is an expert in aircraft trajectory prediction and optimization, especially towards reducing the environmental impact and in developing stochastic models to improve efficiency of the NAS in general. He's also the founding chair of the AIAA Human Machine Teaming Technical Committee. He was co-chair of the National Academies Committee that developed the US agenda for autonomy research related to civil aviation. He received all his degrees from MIT. He is a fellow of the AIAA, RAES, and AgiForce Informs and Sigma Psi. And the topic of today's seminar promises to be super interesting towards increasing autonomous aircraft-enabled mobility. We've all been seeing the growth of urban air mobility and new advances in multiple modes of transportation. So this is highly relevant and pertinent to what we've been seeing. Over to JP now.
Thank you, Lavanya. I don't know. I hope it is truly highly relevant, but we'll see. Good morning, everyone. Good afternoon for those in Europe. Happy to be here, a longtime member of Informs. At one point, I was the chair of the aviation applications section, so many years ago, and been a TSL member for a long time. So always good to be amongst friends. And today I wanted to talk about towards increasingly autonomous aircraft-enabled mobility, and I want to basically talk about some of the things that I think we need to be tackling, which have a sort of OR bent to enable the vision for what NASA and more generally the US is now calling advanced aerial mobility. So they've moved a little bit from urban air mobility to advanced aerial mobility, to recognize the fact that it's not just urban, it's suburban. It's also enabling connectivity to potentially enabling connectivity to the rural areas, for example, transporting medicines, et cetera, and potentially patients to and from remote areas. So I'm going to use the term advanced aerial mobility throughout the conversation today. What I'm going to do, I'm going to talk about what advanced aerial mobility is, because that's always a good place to start, define things. Then I'm going to talk about what autonomy is, because autonomy is, I think, the phrase next after systems engineering. It's all things to all people. I'm going to try to define what I think autonomy should be, or at least what I think it is. And we might be able to quibble or argue about that later. And then I'm going to talk about a couple of projects that we're working on, looking at how we can achieve autonomous trajectory planning and landing, which are two particularly challenging things in aviation. And then I'm going to talk about just opine, rather, on a framework that we could be used to be exploring certification, because that is the big challenge that is sort of the 800-pound gorilla in the room when it comes to advanced aerial mobility. So what is advanced aerial mobility? Well, I'm going to tell you what it is by describing what the world would look like with it. So it's a world where you have primarily aircraft, primarily vertical takeoff and landing, or short takeoff and landing. So that's the aerospace term for the VSTOL, vertical / short takeoff and landing aircraft. Transport passengers and cargo in urban, suburban, and regional settings via a hybrid. So it's going to be a point-to-point plus hub and spoke network. You know, we travel on airlines now where we have to usually transit the hub unless we live in a major city, when it's always point-to-point because it's nonstop. But this network is going to be a hybrid. It's going to be a combination. It's going to be more like what Southwest would have. And if you think about it, Southwest's model was to compete with automobiles and buses at first, right? So you'd expect that to be the case. That is dynamically generated based on demand. So it's not, there will be some schedule, but there will be demand. So you can think about mixing an airline and Uber all in one. And that's going to be particularly fun, challenging in terms of that allocation of resources and pricing, et cetera. So it's great problems there. I'm not going to talk about those, although I could, but I'm going to talk more about some of the air traffic control and vehicle certification problems. And the idea is to get the desired economies of scale. And, you know, everybody would love to be able to have their own vehicle that they pop into and fly across town from work to home and home to work and wherever you want to go. But it gets expensive. Aircraft tend to be a little bit more expensive to operate than cars for a single person. And so you want to have some groupings to achieve these economies of scale. And if you think about it, advanced aerial mobility is a logical outcome for our quest for speed as humans, right? So if you think about it, in the latter half of the 19th century, New York and London looked like what you can see on the top right? There was a fair number of traffic jams at intersections, roads were crowded, and they introduced traffic lights, and that staved off the congestion for a bit. But anybody who has been to New York, pre-pandemic, of course, and seeing the traffic, you know that the traffic lights just kind of keep you at the edge of congestion as opposed to actually reduce it. So what did we do in the major cities at the end of the 19th century? We went underground, right? And if you go to London and you try to ever get across the city with a bus or versus a train, you can do it so much faster on the tube than you can on the bus. And that's because, you know, you have dedicated pathways. So, you know, we went underground, and it's really expensive to build underground. So the logical thing is to go above ground, because all you need is a ground infrastructure, a physical infrastructure, and there's lots of airspace around. So in the early 21st century, we're basically doing that. We're going above ground because we want speed. We want to be able to order something at Amazon and get it in the next hour, or if we had our way the next 15 minutes, but you know, that's maybe we need some supersonic vehicles for that. But so what are the kind of things that people are working on? Well, you know, the top left, people are having single passenger point-to-point vehicles, right? And there are a fair number of them out there. And then in the bottom left, you can see a sort of a multi-passenger vehicle where you could actually, walk down or maybe scooter down or take an Uber to a local vertiport. A vertiport is the phrase we use these days for vertical takeoff and landings. Consider an airport in your neighborhood. And then everybody gets on a common vehicle and then fly to another vertiport and then disperse, right? And it could be, you can think about it like a Uber pool type model, or just basically going down to the local bus stop, all different kind of ideas that people have there. But the bottom line is we're going to have individuals wanting to travel point to point and people grouping together. And all of these are going to require air traffic control, which is the thing at the bottom, in the bottom middle, to manage all of that traffic. Because imagine how hard it would be to manage thousands of vehicles flying over your local city or your local area. Everybody not only transiting people, but cargo, and everybody wanting their different packages delivered. And then the companies that operate them are going to have similar type back office infrastructure like airlines do, to do the maintenance of their vehicles, to do passenger, make sure that if something happens, the passenger gets reaccommodated, or the cargo gets to where it's going to be, and etc. And then on the right, you have sort of two models of how we might deliver the cargo. So the top right is a model that UPS has been exploring, where you use small drones to sort of help the Uber driver deliver in a particular neighborhood, for example. And there's a bunch of papers on that in the literature, and it's in the OR literature about that. And then the bottom right is a model that I am particularly fond of, and I believe is going to win out. Because if you're trying to deliver cargo, and the aircraft is the fastest vehicle in your network, right, or your stable of options to move the cargo, you put the fastest vehicle on the longest link, right? And so we need to have a larger vehicle that can consolidate demand in a local region, and then resupply the local vehicles that you can have the delivery person actually be able to do the nuanced things like say hello, greet the doorman, get the thing all, if you're not there, leave it in the right spot on the porch, all those things which are tough to do with an autonomous vehicle, and leave that last bit, the last inch or the last mile or maybe the last block to the ground folks, and use the air vehicle. Now that's some particular challenging thing, because the bigger the vehicle is, the more redundancy you got to build in, and the certification requirements become very, very difficult. So, but I do believe that that's the way ultimately we want to go, because that is the one that will give us the fastest cargo operations. So with that said, I won't belabor that, because obviously I want to talk about the stuff that we're working on. So I'm going to just summarize what I see as the grand challenges associated with advanced aerial mobility. And these are the sort of the grand challenges when I testified to Congress. I think that was back in 2018, I think, about advanced aerial mobility. These were, for me, what I think of as the big grand challenges. First is that we're going to need greater autonomy in our aircraft. And I will talk a little bit more in detail about that. But the fact of the matter is, I cannot imagine having enough trained pilots to operate all those vehicles with passengers in them, right? And so either you're going to have to reduce the requirements or the training requirements on the people who operate the vehicles, or you're going to go fully autonomous vehicles. Either way, there's going to be greater autonomy in those vehicles that are operated. And then certainly in the cargo realm, you want it to be autonomous, because you can't get the economies of scale that way either. Then air traffic management will require greater autonomy as well. I mean, I don't know how many of you are au fait with air traffic control, but every aircraft that's up there, there's a human on the ground monitoring that aircraft, right? Via radar or via intermittent reports from the aircraft or broadcast ADSB. There's a human monitoring either one or more aircraft for every aircraft in the air. Imagine a city with a lot of vehicles flying around. It's just unimaginable that you could have all of those people hired and trained to do that. It takes 6 years to get full performance level air traffic controller at the FAA, right, from ab initio. And so it's a lot of training required, a lot of skill and required in doing that. And quite frankly, the way we do air traffic control is quite Eulerian, as in you sit and vehicle comes into your space, and then you might deal with the vehicles in your space. And then the more vehicles you have is the smaller the area you can control. And the more the handoff between areas becomes a time-consuming thing. So there's a fundamental limit to how small the area you can actually have people manage. And so it's just, again, not scalable. So we're going to need some autonomy, a great deal of autonomy there. And then, you know, everybody is want to fly from ideally their house to their workplace, or their house to wherever they want to go, or between any point A and B. And yes, when you're in the vehicle, it's nice to just be able to walk out and get in a vehicle. But when you're somebody else, your next door neighbor is getting a vehicle, that becomes a noise issue. That becomes a privacy issue, because, you know, they can actually be flying over your house, seeing into your backyard. So fences don't work anymore. It also becomes a safety concern, right? Because no matter how good the vehicle is in terms of reliability, there is some probability that there'll be a failure, and there's going to be perceived risk. So, you know, people are going to want to have vertiports near to where they want to go and where they're coming from. And these are going to raise privacy concerns for their neighbors and others around them, and for themselves too, in fact. So there's some interesting things to be had there, and where we place the vertiports and how we operate them, et cetera. And, you know, do we have a situation where you get flying rights over my house at 9 to 5 on weekdays, and then you don't on Saturdays and Sundays, right? Or in the evenings, and then how you manage all of that. So there's some really interesting challenges there. And as you can tell, there's some cool OR problems to be had. So, by the way, this talk is mostly about, you know, trying to introduce the problem and sort of define the challenges and define some of the cool OR problems, at least from my view as I see them. And then we're going to need new certification standards for all the vehicles, the systems, and the operators, because the stringent, you know, aviation tends to have the premise is, I'm going to push you through a really, really, really tough paces, and then you get certified, and the risk is so low that we can absolve you of some of the liability. And that's the sort of the model or mantra around certification in aviation. It's not scalable when you have different people producing, you know, hundreds of different types of vehicles and writing thousands, if not millions, of different software code to do different things. And, you know, how do you certify all of that? That's going to be some challenges. And again, that's more of a computer science challenge, but I think something that we need to be paying attention to. So what you can see from the grand challenges here is that autonomy is a key enabler, and you really need to focus on autonomy. So with that said, I'm going to define what I think is autonomy, and introduce what I call the autonomy quadrant, and I'll get there in a moment. So before I get to autonomy, I'd start with automation, and in part because automation and autonomy are often confused. Excuse me, I'll take a sip of coffee here. Automation and autonomy are often confused. So, you know, automation is the replacement of what the human would do by a machine. And, you know, we tend to think of that as being, you know, the higher the level of automation, the greater the autonomy is. And that is true in some sense, but the dot product is not one. So I'm going to talk about that in a little bit. But the interesting thing I'd like to talk about is why are we where we are in aviation in regards to autonomy? And so, you know, as you know, the reason why the pilots in your airplane wear stripes, you know, 4 stripes for captain and 2 stripes for first, 3 stripes for first officer, and therefore so forth, was because aviation grew out of marine operations or ships. And so in the first crew, there were basically 5 people in the cockpit, right? So there was a captain, a first officer, an engineer, a navigator, and a radio operator, right? And so, you know, this is the cockpit of the Boeing 314, which is a very early aircraft, you know, back in the 2030s, right? And what you see is that, it was quite spacious, way more spacious than your commercial cockpit today. And you had all these 5 folks working together. But what happened was, well, in the 1930s, the first airborne auto-tune radio, which would switch from frequency to frequency automatically, came into play. And so after a while, you basically end up with the fact that you didn't need, and then you also had the Loran system, which is a way of actually determining where you were on the globe's surface using some ground-based beacons. And so those two combined, you end up saying, well, I don't need a radio navigator anymore. And so let me go and get rid of the radio navigator because I can have the auto tune. And then later on, they got the Loran system, and they said, well, maybe we can combine the navigator and engineer together into one new engineer. So we went from 5 to 4 when we got rid of the radio operator, and then 4 to 3 when we got rid of the navigator, and because there's no longer need for big chart planning. And then as things went on, we got inertial navigation, which means that the aircraft can actually keep track of its own position using accelerometers and gyroscopes as well. And then it had more computers added. The first Cat-3, as in the ability to land in 0 visibility, 0 ceiling, i.e. you can't see anything, the airplane lands itself. So we got our first computer being able to do that. And so at that point, we could have insensibly gotten rid of the flight engineer position, but people resisted for a while, because at that point you had 3 people in the cockpit, and it was a great parity test, right? So if one person went off the reservation, you could always vote them off the island. Sorry for those people who like to watch reality shows, but that would leave a problem, because when you have 2 people, who wins out, right? So during the 70s, we developed a fully automatic digital control for the engines. So that was a lot of the roles that the flight engineer was doing, monitoring engines and keeping them in the control and stuff. And also they did a lot of crew resource management work to actually figure out how to get 2 crews to operate well together. And finally, we had digital avionics and the FADEC and everything. So we decided to get rid of the flight engineer position, and we've gotten to 2. And this was like in the Boeing 767, 757 area. That was when we really got to 2 crews for big aircraft. And we've been at 2 ever since. And it's been working. You see that little red line there is the accident rate, fatal accident rate, and you've seen it. Even with a reduction of crews, the automation has brought us great safety. Now we're at the point where, economically, it would be great to not have anybody in the cockpit because you wouldn't have to pay them. But also, pilots can make mistakes as well, right? So, albeit the case that when an accident occurs and they don't know what happened, they always get up saying it was pilot error at the end. But the fact is, pilots can make mistakes, and automation and autonomy could help. But the issue is, how do we get there? And so now that we're there, I'm going to ask, what is autonomy? So when most people consider a system to be autonomous if you can complete the specified task without human intervention. So you tell a system, I want you to do this, and it does it. This definition implies that the focus of autonomy is on action. So you define autonomy based on whether the system can act independently. Now, my rule of thumb is that these operational decisions are being made with rules that have been prescribed by the designers of a system and proven to be performed in a specific manner under specific operating conditions. So, but if you think about what autonomy really is, it's the state of being self-governing. And self-governing is not just doing what somebody else tells you to do. Self-governing is being able to decide for yourself. So self-governance requires more than just autonomous operation, i.e. just I programmed you, you go and do what I tell you to do, and you follow the rules slavishly. What self-governance means is that you can make autonomous decisions, you can learn from your experiences, and you develop your own set of rules based on your journey through the experience of life. So one way to test is what I call the 3 o'clock in the morning test. Assume somebody wakes up at 3 o'clock in the morning and they describe the internal state and the external operating condition of an autonomous machine. And they ask you, what will a system do? If you know the answer, that's autonomous operation. That system is not making any decisions on its own. But if the decisions are prescribed and done, but if you cannot with 100% certainty tell you what the vehicle is going to do, that's autonomous decision making, and means that the decisions cannot be fully described despite known parameters. So full autonomy, it requires both autonomous decision making and autonomous operation, which brings me to my quadrant, what I talked about, which is I believe that we need to be thinking about autonomy within the question of who's making the decision and who's acting, right? And so for a specific example, here's a great example of what I call instance number 1 in this quadrant, where the human is making the decision and the human is doing the action. There is no automation associated with glider flying like this, right? On the other side, you have number 2, where the human is making decision and the machine is in action. And this is primarily most of what we do in aviation in a cockpit, which is you have some strategy where you want to go, you make decisions about, what path you want to take. And then you tell the machine, I want to fly this set of links or to get from A to B, and you program it and you say you go, and you sit back and you relax and let the airplane fly itself, right? So that's on the other side, you have, and we do have an instance where the machine makes the decision and the humans literally do the action. And that's in the collision avoidance system, TCAS, traffic collision avoidance system. The machines actually negotiate who goes up, who goes down, right? And now in the newest version, ACAS X, who goes up or down, who goes left or right, right? The machines negotiate, they up, and they have some uncertainty built in the probabilistic tables they use, but the machines do the machine-to-machine negotiation. They tell the pilot act, and the pilots act, right? So that you have instance 3. And by the way, when the pilots don't act, like they did an accident over Poland a few years ago, it actually leads to an accident. So, having that who makes decision and who acts is critically important in terms of achieving safety. And then we're still in search of number 4, but we need to get to number 4 because that's where we're going to have what we have to get to enable autonomous, advanced autonomous mobility, right? So with that said, I hope I piqued your interest. I'm going to talk, like every faculty member, about a couple of projects that I'm working on. What would life be without talking about your projects? And then I'm going to end up and discuss the whole issue of certification, which I think is the biggest challenge and one where we really need some good thinking. And I think the OR community can provide some good help. So, one of the things that in aviation you always do is you always retain your options. So if you're flying an instrument flight in the US or anywhere in the world, you're required to file a flight plan 45 minutes before departure. Typically it's before longer than that, but the minimum time is 45 minutes before departure. And when you're doing the flight plan, you not only have to specify the route you're going to get from point A to point B, but you also have to specify alternates. So if you go to your airport, if you get to your airport and that airport, the weather is poor or the airport, something happens and you can't land, you need to be able to specify which airport you'll go to after that, right? And that's your landing alternate. By the way, just forgive me, I have a landing alternate joke that I have to share. So I flew back from a conference in Europe and I landed at JFK, and I was going to a meeting at I think it was either the Army Science Board or the DOT Transportation. Anyway, I was one of those councils or boards in DC. And so I took a taxi over to LaGuardia, and the weather was really poor at LaGuardia, and there were lots of delays. And so finally, we got on the airplane and we pushed out, and we were on the tarmac for over 2 hours waiting to depart. And the pilot said, well, the weather looks bad here, this looks bad in DC, but we're getting close to our 3 hours, let's depart. So we took departed from LaGuardia, we flew to Washington, circled for half an hour, and they said, well, unfortunately, the weather is too bad for us to land at DCA. We have to go to our alternate. And our alternate is LaGuardia. So I took off, went and gave a tour of DC in the clouds, and then came back to New York. So that's just an example of the fact that you have to have these alternates. And that's all in flight planning. But the other thing that you have to have is you have to have alternates along the route. So if you have an engine failure, for example, you need to be able to get to an airport or a landing for a big airplane, you have to get to an airport. For a small airplane, like a GA propeller airplane, you usually don't really think about it because there's usually a field big enough or a highway or something you can land in. But the fact is, every time a pilot departs, they need to have an alternate. And this is one of the big roles that a pilot has to do before they get off the ground, right? And so so here's an example where, we have an autonomous vehicle transporting people or cargo. When one of the decisions that they have to make is, can I fly this route and is it safe, right? Do I have the right set of alternatives and do I have a good chance of making it there? And more importantly, basically, is my mission a survivable mission, right? So there's one thing to achieve where you want to go, right? Mission success, but there's also the issue of survivability. So we're looking at the issue of survivability and we're saying, okay, let's imagine a vehicle here, which is down like in Milpitas, down in the South Bay in San Francisco, and flying up to a destination, further north, and in San Francisco itself, right? And then you have lots of other traffic coming up. And remember, this is an on-demand thing. So it's not like you have a schedule where everybody says, I'm going to be departing at 4 o'clock. There are going to be people saying, oh, I need to deliver this package, I'm departing the next second, right? So there's a lot of uncertainty in the operating environment. And so the question is, autonomous vehicle must be able to dynamically update their path in moderate to extremely uncertain patterns. And they have to actually, their mission success, their goal one, but they also have to be talking about their mission thinking about their mission survivability. And the uncertainties can be, the usual thing. They can be statistically characterized or bounded for the things that we have data for, right? But there's some things that are really unknown, unbounded, right? Who's going to tell whether Lavanya decides that I want to go over from Stanford to Berkeley, for example, to give a talk, assuming that Lavanya would, I can see Lavanya, I can't see anybody else, I'm picking on her. If we go from Stanford to Berkeley, for example, it's known, it's not known. I mean, you could try coming up with a distribution for that, but it doesn't really make any sense. So there's things that are, the known unknowns, and there are the unknown unknowns. And I know I sound like Don Rumsfeld there, but the fact is that we do have those. And so we need to be able to plan for these. And we need to be able to say, if, for example, a link in my network gets blocked, I need to always be able to find somewhere to land, because I don't have infinite power in my vehicle, because, either whether you're using batteries or other kind of fuel, there's some limited capacity in how long you can stay up. And so one of the things that we want to do then is to formulate this problem. And we have a time-space network where we look at where you want to go, where you want to get to. You have some required time of arrival at that location, and RTA is the term we use for that. And we have times during the day where that location might be operative or inoperative, right? And so those are the sort of segments there. And then you also have other locations, which like that green column there, which are available all the time as alternates, or they might have actual spots where they're not operative either. And so the idea here is, let us, given some motion primitives that capture the dynamics of the vehicle, figure out what's the best path so that we can have a sufficiently high guarantee, as that would be a probability or expected value, that we can always reach an alternate. So you'd like to be able to have a path that you're 100% certain that no matter what happens, well, short of if the engine goes totally, then you probably won't get there. But within acceptable uncertainties on your vehicle side, you can get there, as well as acceptable, whatever uncertainties occur on the exterior to your vehicle. So the mission is to get to a goal landing site versus alternative landing site, estimate the time of arrival, vehicle dynamics, you got to know that, partially known and none. And then we looked at the feasibility of a trajectory, basically looking at the context of whether a cell is blocked or not. So one of the metrics, well, we can think about the robustness of a plan, L, and we can define alpha dt is the probability that the landing site D is available at time t, right? And then we can look at pi as a probability that the ith segment of the trajectory remains feasible in the presence of a disturbance, right? And so with that, we can actually come up with a plan that says, let's look at all the segments along my way and look at the landing sites, and we can actually calculate the probability that everything is clear, right? That's a measure of the robustness of a plan. And then you can also let's look at the total number of feasible trajectories, right? Which is, one of the things is when you don't know anything, just having more options is good, right? Now, obviously, not if you have more of the same option, that doesn't buy you anything more. So the options should be diverse, but the more diverse options you have, given diversity of options, the more options you have, the better off you are, just to deal with general uncertainty. And that's a premise that we explore. So one of the things that we look here is to look at, as you do a time and you look at the trajectories through the network, you can figure out how many paths and options you have at every time step, and use that as a measure of your trajectory's feasibility. So looking at this whole thing of mission success versus survivability, given a point in space and time, we measure the probability of mission success or survival. And so consider you have a set of trajectories L, which are basically one where trajectories that terminate at the goal and trajectories that reach the landing site, right? So we can say a mission is deemed to be successful if there's at least one feasible trajectory that reaches the goal landing site. You can get there. And this is just straightforward. Then you can say it's survivable if there's at least one feasible trajectory that leads to either the goal landing site or an alternative landing site. So you have some way of getting there. So looking at both of these relatively straightforward metrics, we looked at different policies, right? And so we looked at a policy to maximize the total number of feasible trajectories, right? And feasible means that, you could potentially fly it. Maximize mission survivability. Now that comes in with some weighting of, probability that things are, blocked versus not blocked. We looked to maximize the robustness of the trajectory, which we talked about there. And then we also looked to maximize the average robustness of the trajectory, which is sort of an uninformed baseline, right? Where you just basically say, let's just assume that things go the way. And so we looked at that and we did some simulations. Well, that's how life is. And then we looked and we found that if you look at it, basically, as you increase the total number of vehicles, what you see is that survivability is a key policy. Maximizing survivability makes a lot of sense, especially at lower levels of traffic. However, as you get to higher and higher levels of traffic, maximizing the number of feasible trajectories makes more sense, in big part because it's just a matter there of, being able to just respond quickly to things that are happening. And as you increase also the number of unknown unknowns, it just makes more sense to have the policy becomes the number of feasible trajectories as the measure versus survivability. So we looked at those here from this simulation, and then we looked at the effectiveness of, again, the survivability policy and the feasibility trajectories. And just to make sure be clear, just in case I added any entropy in my description, number of mission survivability is a probabilistic weighted measure of whether or not you can get to an alternate destination or to your goal destination. And then the number of feasible trajectories is just basically having options available, regardless, without any weighting. Is just basically a raw number of, I have a number of options available. So we looked at this, looking at the number of partially known intruders. So NP is the partially known, is the number of partially known intruders. And as you can see here, performance as the number of partially known intruders is kept at of unknown intruders is kept constant. As we increase the number of partially known intruders, stuff people you know about, mission survivability still outperforms everybody else. So what does that tell you? That tells you that if you know something about the vehicles that you're going to be flying through, it's better to use the mission survivability. Use the data you know, use the statistics you know, come up with a good estimate of what the mission survivability is and plan according to that, okay? So I hope that makes sense. Now, if you basically then say, I increase the number of unknown intruders, right? The people who just random pop up, at some point, all of that planning to counter the things for the people that you know something about doesn't make any sense, because there's just so much uncertainty that you end up just basically going and saying, I just need to have more options available, right? So you can see this working out quite well. And so you can see here that as the number of unknown intruders, the unknown unknowns gets greater, you want to just go back to having as many feasible options versus a more complex computing a feasible survivability measure. So that's some cool things that I think a good policy that we should be following as we think about trajectory planning. And by the way, this extends also to larger aircraft flying around the world as well, right? So this exploration of problems associated with urban air mobility or advanced aerial mobility could be useful at the larger scale of aviation as well. Now I'm going more slowly than I thought, but so let me speed up. So I'm going to talk a little bit briefly about landing, about one of the other problems that our big challenges is in aviation is, how do I decide whether I should land or not, or abort my landing, right? And one of the things that we think about is the fact that there's a risk of missing the runway, right? But there's also a risk if I decide to do aborted takeoff of running to a mountain or something. And so you need to, typically the way we achieve the desired level of safety is not by putting everything on the vehicle, but by using stuff on the ground and using the humans, using the vehicle automation, and all together to achieve this, this level of safety. So it's really a combination of capabilities rather than just let me make my vehicle totally autonomous. So one of the things that we want to say is, now, if we're going to take the pilot out, right? And we're going to have to rely on the vehicle to make decisions about when to abort, how do we do that? So one of the things that we notice about the way we do missed approach landings or aborted landings in the world is that if our capabilities on our vehicle and the capabilities on the ground and the capabilities of the pilots are better, we allow the aircraft to go lower and closer to the ground before having to make decision to land. And the reason is because we know where our aircraft is with greater certainty, right? Because our instruments that we use are better calibrated, right? They have better performance. Our pilots are specially trained. So we go from pilots, the run-of-the-mill pilots who can probably only do Cat 1 or Cat 2 landings, to very specially trained pilots who can do Cat 3C landings, which is basically you land in no visibility, right? And so the thing I want to take away from this picture, and in the interest of time, I won't belabor it, is that each of these different categories of landings come with a commensurate improvement in the training of the pilots, in the performance of the system, in the calibration of the system. And it also comes with procedures, like you keep the aircraft on the ground further from the runway if you have a Cat 3 landing than if you have a Cat 2 landing, because you want to make sure that the ground equipment have no possibility of interference, right? Because there's no visual cues outside to confirm whether or not there's interference or not. And the key thing about it is these decision heights are based on literally, when do you need external information to confirm that your internal systems are actually indeed operating well enough, right? That's the key thing to take away. And so ceiling and visibility are dependent on the precision and reliability of the instrument landing system at each airport. So why they're so important? Decision heights are basically the point where endogenous uncertainty is so large, i.e. all the uncertainty internal to your system, that a successful landing can no longer be guaranteed. And what we do with the visual confirmation is to say, okay, I can see the runway, I can see my aircraft, my instruments are good, I can continue my landing, right? And so the better you are in terms of your endogenous uncertainty, the lower it is, the closer you can get to the runway. And so if you think about the problem like that, you can think about it as a stochastic reachability problem. And then you can actually do some, low event sampling techniques to help to speed things up there. So it's not a brute force, and I won't belabor that. All right, and so the issue then is, how do we deal with certifying an autonomous system for that? And if you think about it, what we're certifying in that landing problem is the decision about the pilot's decision about when to stop doing something because I don't have an alternative, right? Because you want to go as close to the ground as possible, but you want to keep going as long as you're able to get out, right? And so there are airports in the world like Queenstown in New Zealand where the airport is in a valley. And before you had precision guidance systems, you had to be able to see the airport before you descended in the valley. Because if you aborted in the valley, there was no way to get out, right? Now with RNP, you can actually go into the valley and get close to the runway because there's a way out. And so the point I wanted to make about landing problems, and this is kind of related again to that trajectory planning problem I talked about before. In aviation, you only go as long as you can, as long as you have an alternative. The moment you're about to lose your last alternative, that's the time for you to abort a mission, right? Unless you're 100% certain you can do the rest of it, which is what you do when you look out the runway and you're basically say, I can see the runway, I'm 100% certain I can land, right? And so this decision height, we actually developed a model for thinking about how an autonomous system would make the decision based on its endogenous uncertainty, information that it receives from GPS broadcasts, from intermittent communications from the ground, all the different systems to figure out when should an autonomous system make a decision about aborting the takeoff. And you can see here, I'm aborting a landing, sorry. And you can basically see that based on the accident probability, which ultimately is what we want, the required one of 10 to the -9, right? With a system, and we did all variant, you can basically go down to about 76 feet and make a decision, which is quite cool. And then you can look at different uncertainties. So you can look at, whether or not your communication system might go, or whether or not your GPS, you might lose a signal, or whether this particular thing in your aircraft might go. And you can develop decision heights based on this. And this becomes your decision criteria for your aircraft. Now, the last thing I wanted to talk about is certification, and I'll be quick. And I'll start by saying certification is really hard, right? It's difficult because the world is stochastic, and we cannot enumerate a finite set of conditions to prove things. We cannot guarantee that the system will make optimal decision because it's going to be a learning system. But the question is, are there things that we can learn from how we certify humans, right? Humans are inherently autonomous decision makers, and yet we certify them all the time. So here's one example, which the parents on the call might appreciate. This is a certification of your kids, right? Mine are 14, so I'm somewhere on this S-curve here, on this piece, and the S-curve here, which is you don't trust your kid to make decisions for themselves until you develop some understanding of their decision-making capabilities. So develop some trust in their decision-making capabilities before you give them the authority to operate autonomously. And I hear when they start to drive, that's the ultimate one, but I'm still waiting for that one. But the bottom line is you need to have trust as a leading indicator for your decision to whether or not you're going to allow your kids to operate autonomously. And I don't know about you, but I don't think any parent ever trusts their kids. So there's always a little trust deficit, right? But you get to operate 100% autonomously at some point. So the fact about this is that you don't have to be 100% trusting to let some system operate autonomously. In the military, we have a similar problem. Nobody trusts a private, right? You tell a private, go and do this, don't move, do exactly what I tell you. But as you learn about their decision-making ability, you might promote them to sergeant, right? And then you tell a sergeant, I need you to go and do this, and the details you leave to the sergeant. And then ultimately you become a general, and they don't tell a general, here's how I want you to fight the battle. You say, I need you to win this particular campaign, right? And you need to get it done by this day. And the general then makes the decisions about how to achieve that overall goal, right? And so what you see here is the level that you are allowed to operate autonomously and the amount of decision-making that you are allowed to make on your own, the number of decisions and the type of decisions you are able to make on your own is all a factor of trust, right? And it's more than just trust in the actions, it's trust in the decision-making. So we certify pilots all the time, right? And we do it with a check ride. And the inspector doesn't say, I'm going to put you through every possible thing that could happen in the aircraft, right? The instructor tests a few key things. And what they're doing is to test how you make decisions, right? So Mike Bragg, who used to be at Illinois, a department head, and was the dean at University of Washington of Engineering, he gave me with his story of when he was 16 and he was getting his pilot license. The Czech airman basically opened the door of the 152 in the middle of the takeoff roll. What is he trying to evaluate? Well, he was trying to evaluate Mike's ability to understand his aircraft, understand what was happening, and determine whether was this a critical situation or not. Should I abort or not? All those things are things that we're trying to determine and model the decision-making abilities. So ultimately, in addition to having clear objectives, you must know, autonomous agents must know themselves and their environment. It's kind of like Asimov type laws, right? So you must be able to estimate your own states to a high level of precision or with high confidence. They must be able to do no harm. They must be able to also estimate and determine which actions they're going to take that will result in, won't cause harm to others. And they also have to protect themselves. They need to make sure that they live to fight another day, right? Be able to keep their capabilities above a minimum threshold. So the question is, can we measure these things in machines, right? And there's a whole lot of work about explainable AI and all those different things. My view is, let's just use statistics, right? The truth of the matter is, if I evaluate people over a range of a very varied range of conditions, and 100% of the time, they actually can estimate their own state really well, right? Correctly. They can estimate what's happening around them correctly, right? And they can know what the set of actions that will keep themselves safe and that will get to achieve the goal and do no harm. That's something I can trust. If it can do it, if it can only do it 30% of the time, that's something I can trust. We have to determine a threshold that we are willing to trust. And is that 95% confidence? There's whole legal issues around that, but I think we have to think about this from a Monte Carlo framework, a sampling framework, low frequency event framework. And of course, you lead to the end. What should the machine do if there's no feasible solution? Well, always make sure you preserve an option, right? And that becomes the thing. Otherwise, we basically turn it over to some appropriately trained, evaluated autonomous agent, the pilot or the ground thing, to make an appropriate response. So with that, I'm going to stop and basically say, look, advanced aero mobility is here. As Lavanya said, it's all over the place. There's so much activity. Autonomy is a key enabler. Full autonomy requires autonomous decision-making and autonomous operation. And certification is the big challenge. And I think we in OR have a a key role to play there, both from the management science and from the operations research side of, and informs, and both from the management science and the operations research side. So let me stop there, and I'm sorry for going over so long, but hopefully it was useful.
Thank you, JP. I'm going to ask the participants to enter their questions in the Q&A box, or you can raise your hand. The Q&A box is the easiest one. So if you can just click the Q&A and enter your questions in there. So let me begin with a question. So we think about, like, when you think about ground autonomous vehicles, we think about vehicles like Tesla, companies like Tesla and others, where they have the option that, well, we have autonomy, but the human is the fallback in a sense. And that's different, clearly, possibly, at least in the extreme of aviation, where we want these vehicles to be completely autonomous. But I'm thinking about what are the big differences between ground-related autonomy and aerial autonomy. When you think about top two, of course, there are similarities, but what are the top two? So
I will say, I actually don't think there are that many differences in the sort from a methodological and an engineering point of view. I think there's a philosophical difference there. First of all, let me just say that I don't think you're always going to require an aviation that is going to be fully autonomous, right? I mean, there will be a role for humans, and that's part of the reason why I founded the Human Machine Teaming Technical Committee in the IAA, because I do think this is a partnership. But what I will say, however, is that the model where when the machine can't do it anymore, you turn it over to the humans and say, here you go, is ultimately a flawed one, because there's this thing called situational awareness, right? And a human must have a mental model of what's happening in order to make their decisions. And they must also be up to date on what the state of the system is. And just turning something over to a human and say, okay, I can't do it anymore, here you go, has been shown in aviation to be a recipe for disaster, right? So, you know, again, that's part of the reason why we focus so much attention in aviation on human machine teaming and understanding how they work together, because we know from past experience that just basically saying, let the machine do it, and when it can't do it anymore, you know, flag a light and say over to you, you know, is not really a recipe for success. So that's one thing. And the second, so I caution folks in the automotive world to really think about this as a human machine teaming problem, and not just about the machine will do everything. Again, the problem is no different, but again, the philosophy is different in the following. In aviation, we have target levels of safety, and we achieve those targets or levels of safety by looking at what's on the vehicle, what's on the infrastructure that's fixed, what the human can do and what the machine can do. And we look at, said, how in combination do we achieve that system level of safety? And that landing problem is a great one, right? In an instrument landing system, you have an obstacle clearance zone, which says you can't build buildings above a certain size or a certain height in these areas, because we need to have clearance, because the aircraft is uncertain. So we want to make sure that we preserve the space. And if you have a Cat 3 landing, you have to keep all these aircraft and vehicles and trucks away, because they could interfere with the dipole antenna and cause the aircraft, the signal to drift and cause the aircraft to drop. And we have, you know, you need to have the pilot to be able to see the runway by a certain height, because the instruments on the aircraft don't have the precision to go below that. So it's all in combination to achieve the target level of safety or the required level of safety. There's a philosophy in the automotive world that we're going to put everything on the vehicle, and the vehicle is going to do everything by itself, right? And I think that's flawed. I think we need to start looking at how do we combine the infrastructure on the roadways, build the infrastructure in combination with the vehicles and the potential and the, not necessarily maybe the driver, but the part where the people who are on board, who could provide information, exogenous information that could be helpful. How do we combine all of those, like we do in aviation, to achieve your desired levels of safety, right? And so that's my big thing. And, you know, and there's an extreme case where I won't say which one, of the automators, vehicles, automobile manufacturers who's pushing autonomy, believes that vision is the only way, right? And we know full well that, I mean, especially folks like in the Midwest, when you get a snowstorm and it's blinding, yeah, I don't care what vision system you have, it's not going to work, right? So, you know, ideally, you'd like to have a multi-sensor type capability to get different information. So,
all right, thank you. Audience questions?
Hey, no questions, is that right? Either was really boring or really good, but no in between for sure, because there's no questions.
I think there are a lot of, I think this is a huge problem. That I think that is where creating blocks of questions to design such a system, because I was thinking, even if we have to think about the kind of trajectories, it would be useful in the kind of situation we're thinking about, that a human, let's say a human is operating this, even then they have a set of trajectories that they can use, that let's say the machine computes for them. They have options, they understand that, while at the same time they're also aware themselves and using their own intelligence for the environment and updating. But it sounds like there is a need for real-time computing, which is higher, much higher than what we are looking at. And also the sensing and other things have to be integrated from the systemic point of view to the individual point of view, the entire hierarchy.
Right. I think that the lesson is this is a system solution. It's not going to be, you know, I'm going to build this vehicle and it can just operate like putting a car out there on the road or putting an aircraft out there because I have a pilot in there. You have to really think, you know, what are the capabilities of the machine relative to the human? And we are far way away from having a machine that is going to be a drop-in replacement for a human, right? And so they will have strengths, and machines will have strengths and weaknesses, and then they're going to be different from the human strengths and weaknesses. And we have to think about how do we design the system to accommodate those.
Yeah, I think in this we can also see how to, again, you know, incentivize or influence human behavior or what their needs are, even the on-demand mobility. Similarly, like what we want to do on the roads, but think about, given safety considerations, given other things of what the system is, maybe the FAA or someone wants to say, I want to create incentive structures differently at every point. So seems like there's a huge wealth of OR related questions.
Oh, there are lots and lots. And, you know, and NASA is funding a fair bit of research. So there's also lots of, I think, potential research funding as well, right?
Wonderful. Yeah. Okay, so we're a little over time if there are no questions.
All right, I bored everybody to death, so all right.
Well, thank you, JP. This is really exciting. Thank you, everyone, for coming, and look forward to the next TSL seminar. Bye.
Bye.